wheel. For me, it's like, so what? I don't pay for my own food for this whole wheel. I pay for it. Bug him. Oh. Yes. Yeah. Yeah. So, because to me, the little things like that. But anyway, I have decided that
Was it a New Year's resolution?
no, it was, oh my gosh, I'm 8 months behind resolution. I got sitting half down on the table in the living room like that. There's some other things that
Crazy stuff. I did send Patrick a note this morning to ask him if he would help me with for dog shoe, and I apologize. I said, I've never been there.
Yeah.
I said, I can do the airfare as long as you're
I think it's cool. I actually, if we have time to break, he's because he asked you to do his study.
I don't know if he's been emailing. So I didn't open his email, but
He wanted to do a study, but it's only it looks actually great. Oh, you should absolutely do it on play.
a dissertation like that. But the dissertation is 30 minutes, but I can do it.
Do you have your PDF copy? Because you need to be able to either print it and do it on paper, or I'm just going to highlight the PDF.
Oh, no, I'm working on it. I just recently been able to do that on my It's to the point now where it's now. But Bill's dissertation, I've been organized that way.
So, good morning, ladies and gentlemen. So, this is the second day of the NasBASE conference, and thanks again for coming and participating to success this event. So, now we have the third exciting keynote talk by Professor Lionel. He's a professor and our chair in software verification and validation at the Security Center at University of Luxembourg for Security, Reliability, and Trust. He also acts as vice director of the center. Lionel started his career as a software engineer in France and has conducted applied research in collaboration with industry for more than 20 years. After moving to Luxembourg in January 2012, he was leading the center's Center for Software Verification and Validation at Simula Research Lab, where he was leading applied research projects in collaboration with industrial partners. Before that, he was on the faculty of the Department of System and Computer Engineering at the University in Ottawa, in Canada, where he was full professor, and he had the Canada Research Chair Term 1 in Software Quality Engineering. He also has been the Software Quality Engineering Department head at the Frontier Institute of Experimental Software Engineering in Germany, and worked as a research scientist for the Software Engineering Laboratory of NASA and at the University of Maryland here in the US. Lionel was elevated to the grade of IEEE Fellow for his work on the testing object-oriented systems. He was recently granted the IEEE Computer Society Alignments Award and the IEEE Reliability Society Engineer Award of his work on model-based verification and testing. His research interests include software testing and verification, model-driven engineering, search-based software engineering, and empirical software engineering. Lionel has been on the programs on the program committee, steering committee, and organization committee of many international IEEE and ACM conferences. He is the co-editor-in-chief of the Empirical Software Engineering Journal, and is a member of the editorial board of Systems and Software Modeling and Software Testing, Verification, and Reliability. So let us welcome again our speaker, Professor Lionel.
Good morning. I'm glad that nobody's from because, given the pretty bad cold I have, I don't want to create a new epidemic in Michigan. So I will try to do my best to talk clearly despite my sore throat. And, I made a few drawings along the way. Let me try to set this up. Can you hear me well?
Yes.
So, when I give a talk, I always feel that I have to be a little bit, an ambassador for Luxembourg. Because, for first, Luxembourg is not part of Germany. I want to make that clear. It's an independent country. And despite being one of the smallest countries in the world, it has 3 official languages, plus English in the university. 50% of its population is foreign. And it decided for some reason that ICT, security, and reliability was going to be a national priority. And it established a research center, which is the center where I'm working in right now, the SMT Center, with more than 230 scientists. Something strange happened. Anyway, it's a European headquarters of companies like Amazon, Skype, and in the automotive domain, Goodyear and Delphi. So actually, a lot of companies have set up R&D activities in Luxembourg. So, but more interestingly, this is the only Grand Duchy in the world, remaining Grand Duchy in the world. We are a member of NATO with 1,000 soldiers. It's not size that matters, quality, you see. And 2,000 policemen in the whole country. Just to show you how safe we are. We don't need more. The country was occupied by nearly every other European country, including France, Russia, Austria. So we are used to dealing with foreigners in a variety of ways. And the Grand Dukes of Luxembourg have contributed Holy German emperors and even kings of Bohemia, the current Czech Republic. Don't ask me why or how this is possible, but And more importantly, we have the highest sale of alcohol per capita in Europe. So you see, this is a very small but highly noticeable country in many ways. And this is a national beer, which I do not advise to anybody visiting. And our Grand Duke. So now, regarding the topic of today's presentation, the term verification is used in a variety of ways in software engineering. So I use it here in its widest sense, that is defect detection, okay? As opposed to, for example, formal verification, which is based on proving properties. Testing in practice is the most common verification technique for a number of reasons. Testing is about systematically and preferably automatically, if you want to scale, exercise the system such as to maximize its chances of uncovering latent faults within time and resource constraints. There are other forms of verification as well. Design time verification, and after deployment, what people sometimes call runtime verification. But in practice, they are much less used for a variety of reasons. One thing also which is noticeable is that despite decades of research, about 40 years, I would say, or more now, research hasn't had a very significant impact on software verification practice. And there are a number of reasons for that. Probably the applicability and scalability of research results hasn't received enough attention. So what I mean by applicability and scalability? By applicability, I mean, can a technology be efficiently and effectively applied by engineers in realistic conditions? By realistic and only universal, a technique may only apply for a certain type of system in a certain domain. As we will see through the example projects that we go through, context and domain matter a great deal in terms of determining what solution will be applicable. Scalability is also an issue. It's probably the main issue I have faced in the last 20 years when working with industry. There are different types of scalability. You have human scalability, can people perform their task? And you have computational scalability. Can your tool scale to large artifacts, large models, large data sets, large input spaces, and still provide useful support within reasonable effort, CPU or memory. And the reason why I'm mentioning this is that in all the examples that we provided in all our research projects in our institute, we always focus on those two features. So our focus here, as opposed to formal verification, is how can we, in an effective and efficient manner, uncover as many critical faults as possible in software systems within time constraints while scaling to artifacts of realistic size. And what realistic means depends, of course, on the context and the domain. I mean, there is no universal definition of what realistic means. So the talk outline will be as follows. I will tell you a little bit about how we work in our center, how we perform research, so that you better understand the example projects I will go through. I will give you a number of example projects, and I'll try to draw lessons learned and identify similarities and patterns across those projects in terms of the solutions we've adopted and how we solved scalability and applicability issues. So just quickly, the context. So SNT is a research center whose objective is to perform research in collaboration with public and private partners. So our job is to have impact through our research. We cannot just publish papers. We actually must find real solutions to real problems. My lab is about 25 scientists, large. We work with 6 partners, including 2 partners in the automotive domain. And today, I decided to focus on projects in the automotive domain because we're in Michigan, and I was hoping to attract the attention of the local industry. But I'm not sure how many people from the local automotive industry are actually attending the talk today. So what we try to do is that we try to follow different paradigm of research than what you typically find in universities. What we do is actually I would advise anybody here in the room to read a very interesting article by Ben Schneiderman, published in The Atlantic in 2013, where he is exposing his views after 40 years of research in terms of how to perform high-impact research. It's a very interesting article. And basically what he's saying is that in applied disciplines, in particular in engineering disciplines, research, whether it's long-term basic research or shorter-term applied research, should take place in a context. That research taking place in a vacuum doesn't make much sense. Why? Because context factors determine applicability and scalability of solutions. So he was advising basically that research somehow takes place in the context of innovation and development, so that it can be driven by problem raised by actual engineering and innovation. And so that you could produce at the same time publishable research results, but also focus on practical solutions that have a market. Basically, what he was saying is that, and this is also my experience in the last 20 years, is that if you perform research in a vacuum, you are very unlikely to find a solution that will fit in any realistic context. And in practice, this is the way we work with our partners. It's not really surprising, I guess. We identify and prioritize large problems. We decompose those problems into sub-problems. We re-express those sub-problems in scientific terms. We review the state of the art, we identify gaps. In software engineering, the gaps are always very large, no matter the topic, between research results and practical needs. So usually we don't have too many problems to find a research topic. And eventually we go through some phases of initial validation, possibly in artificial settings. It's not always possible. And eventually, when we have a certain level of confidence that our solutions will help, we move to a more realistic validation in the context of pilot projects, for example. And then we iterate. So let me go through the first example. So here I'm going to talk about testing closed and open loop controllers. As you know, in the embedded domain, and in particular in the automotive domain, a lot of devices a lot of the engine, the braking system, the cruise control, a lot of physical devices are controlled by software components called controllers. There are different kinds of controllers. Two broad categories are closed and open loop controllers. I'll get back to it. So, but this doesn't apply only to the automotive industry, in robotics, in aerospace, in the satellite industry, manufacturing, etc., etc. You have increasingly complex controllers. In the automotive industry, those controllers run on electrical control units. And those electrical control units contain increasingly larger amounts of software, and usually millions of lines of code. And they are getting increasingly complex because the automotive standards are getting increasingly complex and demanding. There are more and more requirements in terms of safety, reliability, the environment, fuel consumption, etc. And of course, the problem is, how do you test such software? It's not obvious, and I'll get back to that. Well, in fact, how you test it depends on the nature of the software. You know, on those electrical control units, you have computational software, you have controlling software. In the controlling software, you have software that has a state-based behavior and software that has a purely continuous behavior. And what is interesting, you will see, is that even if you restrict yourself to controllers, the way you test those controllers is completely different depending on their behavior. And it shows how the specific characteristics of the software under test and the context matter a great deal in terms of test strategy. So let's start with closed-loop controllers, and then we will move back to state-based controllers. So, how do people develop software in the automotive industry? It's not exactly the same as in other industries. There are three main phases. In the first phase, it's called the modeling in the loop stage. Everything is a Simulink model. I'll tell you a few things about Simulink in a minute for those who are not acquainted with it. That is, the controller is a Simulink model. The environment, the physical environment that the controller is acting upon is a Simulink model. Then eventually, the code of the controller is partly generated, partly written, but the environment is still a Simulink model. And in the last stage, hardware in the loop, the controller is executed on the actual hardware platform plus a few physical simulators for the things that cannot actually be in the loop, the pieces of hardware that cannot really be in the loop. And here, of course, you can run many test cases because everything is a model. So here, testing is cheaper. Here, testing is extremely expensive because you have to very often manually set up the hardware for every test case execution or the simulators. So here you can run, as many test cases as you have computational power. Here you are extremely limited by manual power or manual resources. So Simulink is simply, for those who don't know it, a data flow-oriented languages where you have data flows and you have blocks, and the blocks perform usually mathematical operations or logical operations. They can contain differential equations, difference equations, all kinds of operations that are available in libraries. And it's a very common language in the embedded world, and in particular for people who are developing controllers. So at the middle stage of development, you have the controller. The controller sends output signals to a plant model or an environmental model. That model is simulated in order to determine, for example, the state of the device being controlled, whether the position of the valve, the torque of the engine, whatever is being controlled, the position of the missile, And the output of the plant model is fed back to the controller, which then decides what is the next output signal to be sent. And this is what I call the feedback loop. There is a feedback loop which basically helps the controller based on an input, which consists of the initial desired value for a device, for example, the position of a valve, and the final desired value, the final desired position of that valve. basically send signal to the plant model, which then brings the position of that valve into its initial position, and then its final position. But of course, the actual position of the valve or the actual position of the device being controlled does not exactly match the initial desired value and the final desired value. There is always, as you can see, a certain degree of noise in the actual position of the device. But this is the test input and this is the test output. Of course, in reality, things are a bit more complex because the test input is not just the initial and final desired position of the device being controlled. You also have a lot of configuration parameters, which increase the size of the input space to a large extent. Why? Because controllers are supposed to run on different hardware platforms. And typically they are configured to the specific hardware platform on which you want to execute them. For example, controllers may have to be configured for different car engines. You know, those automotive companies do not develop a single controller for each car engine. Okay? So, when we are talking about testing controllers, when you test properties. What properties are we interested in? Okay? Well, it was not obvious when we talked to engineers, because engineers had not really formalized what they meant by a working controller. They would look at the results and decide whether they were okay or not. But we had somehow to formalize that in order to be able to automate testing. And we realized there were three key properties for engineers. Responsiveness, how fast you get to the final position. Smoothness, whether you get to the final position by creating large bumps. And this is very important in order not to damage the hardware. If you have large bumps here in converging toward the final position, let's say, assume, for example, you are controlling a valve, then the valve is bumping against other metal pieces. And that's not what you want because you will damage the valve. And stability, whether you converge toward the final position in a stable manner. So this became basically the properties being exercised and tested. Our test objectives, if you will. And of course, being in a search-based software engineering conference, what did we do? We decided to use Meta-Heuristic search. So basically, we have a set of inputs, final initial desired position, and what we want is to use search to find worst-case scenarios. Worst-case scenarios with respect to stability, smoothness, and responsiveness. Of course, worst-case scenarios may turn out not to validate requirements, okay? In terms of stability and etc. But that search is rather complex because the controller's behavior is complex. The controller's behavior is specified by differential equations. So the landscape here can be extremely complex. Okay? And I'll show you some examples in a few minutes. Another issue, of course, because the input space is very large, is scalability. So you will see how we handle that. So if we talk about search, we need fitness functions. Well, I'm not going to go into the detail, but it's pretty intuitive. If you have a signal like this, well, its fitness will be higher than if you have a signal like this in terms of smoothness. So we try to quantify those requirements through our fitness functions. So the search space, to summarize, are the initial desired values, but also the configuration parameters, even though I will leave that apart for a few minutes. We consider a number of search techniques. In fact, it turned out that single-state search techniques work better than population-based search techniques. You will see why. The main reason is that computing our fitness functions is very expensive. This is our main scalability problem. The reason why it's expensive is that when you evaluate a solution, or you compute the fitness of a solution, you have to basically simulate the simulated problem. And this is, it comes at a high price. So What do we want to achieve with this? First, we want to find problems, as many problems as possible, in the near stage, in the modeling in the loop stage, so that we decrease the cost of testing and then we decrease the cost of correcting bugs. Second, we want to take the worst case scenarios we find during the near stage, and we want those worst case scenarios to become the test cases for the hardware in the loop stage. Remember that in the hardware in the loop stage, we can only run a very small number of test cases. So we want to make sure we run the worst possible scenarios. So we use the result of near testing to decide what to run at here testing. Okay? So we developed a tool, we developed a technology that is being used now by Delphi, our partner on this project. There are two phases in the search, in fact. There is an exploratory phase where, and here, follow, I'm simplifying. Here you have the final desired position, the initial desired position, and basically in the first stage we explore the input space and we identify high-risk areas, which are denoted in red here. And then the domain experts look at it and decide what part of the input space represents a higher risk. So for example, if the controller is controlling a valve, the part of the space where the valve is closer to being closed, or is is nearly closed, is more high risk than other parts of the input space. And once they decide what are high risk parts of the input space, we basically perform more exploitative search on those parts in order to find worst case scenarios, such as the blue scenario here, where you have large bumps. So here is an example case study in which we worked, just to make it a bit more concrete. This is a bypass flap controller that basically helps control the air pressure in the engine by controlling a bypass flap. It sounds very simple, but you would be surprised to know that this is a simple model with 34 subcomponents and with 6 abstraction levels. You know, it's very surprising, but that's how quickly complex those simulink models get. So in order to evaluate our testing strategy, the first thing we did was to seed realistic errors in the simulink models and find out whether our tool would automatically detect scenarios triggered, or worst case scenario triggered by that, the fault we had seeded. And the results were pretty good. This is an actual example where we generate a scenario with high instability. And then, of course, we analyzed a number of actual simulink models. We found worst case scenario that we showed to our partners, to the engineers at Delphi, in order to tell us whether or not, you know, those scenarios were acceptable for them. We looked, of course, at the degree of randomness in our search by looking at how the fitness increased over a number of iterations. And of course, as for every Meta-Heuristic search, there was a degree of randomness. We compared the results of our best algorithm, which was a single-step search algorithm, 1+1 in this case, with random search. We compared the speed of convergence, the random variation around the average, and in order to make sure that the problems we were tackling were not trivial, that they required search, etc. And the results could be summarized as follows. First, we found worst-case scenarios that were much worse than anything our partner engineers were aware of. And I'll show you that in a few minutes. Of course, the results were much lower than random search, our baseline. We used then those worst-case scenarios to run on the hardware in the loop platform, and this turned out to be very useful for the engineers. But there were a number of open issues. I won't go through all of them. Simulations are expensive. Computing the fitness is expensive. Therefore, the search was extremely expensive. Configuration parameters that I've ignored so far increased greatly the size of the input space. And moreover, the search algorithms, in fact, were at a varied level of effectiveness depending on the part of the input space they were in. In some part of the input space, you have a clear gradient. In other parts, the landscape was much more complex. So ideally, we would need a more exploitative search here and a more exploratory search in that part of the space. So we had to devise heuristics that were specific to the problem to be handled in order to decide how exploratory should be the search depending on which part of the input space you were in. Okay? But let me now focus on configuration parameters. So I told you, this makes made our life much more difficult. This was a typical scalability problem. I talked about scalability before. Here's a very good example. The good news is that not all configuration parameters matter for all requirements, for all objective functions. So what we did is that we changed the search process by first doing dimensionality reduction to identify significant input variables for each type of requirement in order to reduce the input space. Then, in order to help visualization, because of course we could not use heat maps anymore to help engineers visualize the high-risk areas, because now we are in higher dimensions. We used regression trees, and I'll show you in a minute how this helped us visualize high-risk partitions of the input space. And we use what I call surrogate modeling to predict the objective function when we could, instead of actually running the simulation, and so as to decrease the cost of the search. So in terms of dimensional reduction, we use sensitivity analysis and more specifically elementary effect analysis, which is a very optimal techniques in order to identify the effect of input variables with a small number of data points in the input space. And I'm not going to go into the details, but this is typically used to identify non-influential inputs in computationally costly mathematical models. So we use the observations that were simulated during the exploratory step of the search in order to perform EEA analysis. And then we computed the sample mean and the standard deviation of each dimension in terms of its effect. And basically, if a calibration variables, here you have Cal 5, Cal 3, those are calibration variables. If a calibration variable was close to 0 in terms of mean and standard deviation, then that calibration variable was considered irrelevant for a given requirement. So we managed to reduce the dimensionality of the input space that way. Then in terms of visualizing high-risk partition of the input space, we use regression trees where we try to predict, smoothness, stability, for example, using regression trees based on the desired positions in input and the calibration variables. And then we showed those regression trees to engineers, and they could identify which of the leaves of the regression trees had significantly higher needs. And those were, of course, potential high-risk areas. Okay? But for that, of course, you need a regression tree that accurately predicts your requirements. And the third part of the solution, as I said, was surrogate modeling. What is surrogate modeling? Let's say that in the course of the search, you're in position A, this is your landscape, and the search suggests that you should move to B. Then you have three possibilities. Either you don't move to B, or you move to B, you run a simulation, or you move to B and you don't run a simulation. And what you do basically is that, we build a multivariate prediction model that tries to predict the fitness of a given position in the input space. If we predict higher fitness for the new position with a high level of confidence, then what we do is that we move, but we don't run the simulation. If we predict a lower fitness with a high level of confidence, we don't move, of course. If we predict a higher or lower fitness, but the level of confidence is not sufficient, we move, but we run the simulation. Okay? And remember that the simulation is the most computationally expensive part of our search. Okay? So we tried a number of modeling, statistical and machine learning modeling techniques, In the end, a polynomial regression of degree 3 turned out to work very well. Why not? So that's what we use. We also looked at whether dimensionality reduction helped us also build better prediction models. It did. And of course, we looked at whether with our strategy to scale up, whether we managed to either get better results or faster results. And we got faster results for responsiveness, much better results for smoothness, but our proposed strategy didn't bring any benefits for stability. And one possibility is that we didn't manage, well, the main reason actually, is that we didn't manage to build accurate prediction models of fitness for stability. We haven't found a way to build accurate prediction models, which was the main reason why there was no gain for stability. Of course, there are many other techniques, machine learning techniques we haven't used, we haven't tried, which may turn out to produce an accurate prediction model for stability. Maybe more importantly, our approach was able to identify critical violations of the controller requirements that had neither been found by aerial work nor by manual testing. By aerial work, I mean the work without surrogate modeling and dimensionality reduction. So, for example, for stability, they had never found any problem by doing manual mill testing. We didn't find any problems when we used fixed configurations of the controller. And then when we considered all possible feasible configurations, we found a significant deviation into the stability. For smoothness, we found larger deviations when considering all configurations than without. And for responsiveness, we found much longer response times when considering all feasible configurations. So what that says is that scaling to the entire configuration space was extremely useful because we found much worse scenarios. Now, I told you about closed loop controllers. Now let's look at open loop controllers or state machine controllers. You might tell me, well, those are controllers, why is that different? Well, you will see how small differences have a huge effect on your testing technology and test strategy. So one, sorry, that's going to be a tough one, speaking for 1 hour. The first big difference is that closed loop controllers have continuous behavior, purely continuous behavior. They are specified by differential equations. Those controllers have a mixed, discrete, continuous behavior. And usually they are modeled by so-called state flows, which is a dialect of state machines for Simulink. Okay? And this is an excerpt for a clutch controller. You can see that, of course, it has discrete behavior, but it has also time-dependent continuous behavior. This is the output signal of the controller, which is a function of time, for example. However, the good news is that the simulation is much quicker. We can run many, many simulations. Why? Because we don't have a plant model to simulate. We don't simulate the environment. There is no feedback loop. But the problem is that when you have no feedback loop, you have no oracle. You have no test oracle. You have no mechanism to compare the desired position to the actual position. So this has huge implications, because that means the main testing cost is the manual analysis of output signals. People have to manually look at output signals and decide whether or not they are okay. So all of a sudden, our testing problem becomes a test suite minimization problem. We have to minimize the number of test cases we run and that people analyze. And the challenge, of course, then is test selection. Which test cases to run? So it's amazing how a single detail completely transforms the problem. Yeah. So typically, you have inputs as before, and then you have an output signal that may look like this. Those usually represent discrete jumps, which usually capture state transitions. Okay, yeah. And then those slopes usually represent more continuously changing signals over time. So we can see here that we have a mixed, discrete, continuous behavior. So in those open loop requirements, you have three types of requirements. Discrete requirements, like this one. The engine speed and temperature should fall inside certain ranges. And if they fall in those ranges, the clutch should eventually be engaged. There should be a transition, a state transition to an engaged state. We have a requirement, timeliness requirement. Moving the clutch from disengaged to an engaged state should take around 6 milliseconds, for example. And we have continuous dynamics requirements, which are quite specific, you see, to controllers, where we say, for example, the clutch should move smoothly without any oscillations, and it should not bump into the crankshaft or other physical components close to it. Okay? So this is a requirement on how the output signal should change over time, if you will. So we tried, I'm not going to go into a lot of details, but we tried different test selection strategies. Some were typical software test selection criteria, like achieving state coverage and transition coverage in the state flow. This was our baseline, our comparison baseline, if you will. Then we had greedy algorithms, research algorithms trying to maximize input diversity or output diversity. We can maximize output diversity because simulation is inexpensive. That's why we can do that. And more interestingly, we use search to define so-called failure-based selection strategies. And this, you are going to see in a minute, are in fact techniques that are based on properties that are specific to state flow controllers. So we devise a test strategy that is specific to that domain. So the first one is trying to maximize output instability. So what we want is to find worst-case scenarios so that the output signal shows a high degree of instability. Okay? And this, of course, is not desirable because it leads to hardware damage. Another thing is that we want to find worst-case scenarios that create discontinuities. What is a discontinuity? You see one here. It's when, for a given point, there is no left or right continuity. Okay? So at point A has no continuity on the left and no continuity on the right. And so such signals create fast, short duration changes in the signal. And this is also not desirable in such controllers. Typically, such mistake results, for example, from incorrect conditions for transitions between states. That is, you enter a state and you exit the state right away because there is a mistake in the transition condition. So we ran a number of case studies. Two of the case studies were provided to us by Delphi, our automotive partner. And the last one is a public case study on the Simulink web pages, but it's not very interesting. The public domain case studies for Simulink models are really simple and not very interesting. We do it because that's the only case studies we can make public, but it's not interesting. So the first two basically control a clutch position, which is the example I used before. The second one controls an engine torque. And the last one, the publicly available one computes a missing position. So we ran a large experiment. We took models. We asked the engineers at Delphi to seed realistic faults. We had 75 faulty models. For each selection algorithm and each model, we ran 5 test suite sizes. We varied the size of the test suite from very small to quite large. Large given the context, given the fact that engineers have to analyze manually the output of every test case. In the end, we ended up executing 225,000, I'm missing a zero here, test suites It took about 16 hours of simulation. And in the end, we analyzed the fault revealing rates of the different strategies, the different testing strategies I mentioned, based on coverage of the state flows, input and output diversity, output stability, and output continuity. And the conclusions were that all test selection algorithms fare better than input diversity. Sorry, AR stands for adaptive random, but in fact it's input diversity. Output diversity, output stability, and output continuity perform better than the criteria based on state and transition coverage. And overall, output stability fare better than the others. But those three strategies, output diversity, output stability, and output continuity, were somewhat complementary and could be used together as test strategies. I'm not going to go into the details, but of course, generating failures is not enough. You have to find faults in simulink models. So we also devised a technology and a tool in order to help with fault localization in simulink models, so that we, based on test execution coverage reports and the computation of execution slices in simulink models, we could provide a ranked list of suspicious blocks in simulink models. And that's it for the testing of controllers. So I gave you a quite detailed example. I'm going to give you a second one, and then browse very quickly through a number of other examples, and then draw conclusions. So the example I had before was a test automation example project. The goal was to do automated testing at the near stage. Now it's a design time verification example, also in the automotive domain. So here, the goal is entirely different. As you know, in the automotive industry, development is distributed. And usually there is a system integrator who is supposed to take all the executables and integrate them on the electrical control unit. And the system integrator is responsible for the result of the integration. It's responsible for ensuring, for example, that they never run out of CPU, that critical task deadlines are met, etc. And it's not obvious because, for example, if we take two stakeholders, the car makers and the part suppliers, they have different objectives. Those guys here, they develop software that is optimized for their specific hardware. They provide executables to the system integrator or the part supplier. So what happens? Those guys have different objectives. The car makers, what they want is an effective execution and synchronization of executables. They want to make sure that executables that exchange data, for example, exchange data in a timely manner, to have always up-to-date data. Yeah. But on that side, what they want is an effective usage of the CPU time. They want, for example, to decrease the cost of hardware. They want to make sure they will never run into problems, in terms of lacking CPU while executing a critical task. So those guys want executables or runnables, as they call them, to execute simultaneously or close to each other in time, every so often, or in a certain order. And those guys, they want to execute runnables in such a way that the CPU usage remains as low as possible, or the maximum CPU usage remains as low as possible. Well, of course, those two objectives, there is a tension between those two objectives in terms of scheduling executables. So, moreover, they don't provide source code to each other. They only provide executables. So they have to find a way to exchange information in a systematic way about the executables they are providing to the other. So there is the so-called AUTOSAR model, which is an automotive standard that specifies what information you should provide when you provide executables. The priority of the task, the execution time duration. Yeah. And then usually the system integrator has to develop glue software and integrate all the executables and ensure that the result is reliable and safe. So in that particular case, in the automotive industry, for real-time software on ECUs, people use static cyclic scheduling. Static cyclic scheduling is a simpler form of scheduling where you divide the timeline into intervals and you assign executables to intervals. Why do people do that? Because it's more predictable and more analyzable. That's typically what people do. The challenge is that you have to assign executables to time slots in such a way that you ensure that you don't run out of CPU and you respect synchronization constraints. And at the same time, you want to reduce the maximum CPU time used across all time slots. So for example, this one is better, this schedule is better than this one because it's more balanced in terms of CPU usage. How do we do that? Well, we use search. And what is the search problem here? The search problem is to assign an offset or a delay time to every execution of every runnable along the timeline in such a way that you satisfy those objectives. You respect the period of the runnables, you respect the time slot, that is, you don't spend more CPU than you have in the time slot, and you satisfy, to a certain degree, synchronization constraints. So that becomes a search problem. Hopefully, you can go from this, something like this, to something like this, ideally, in terms of CPU usage over time. So we use the number of search algorithms that are suitable for discrete spaces, such as taboo search, and hill climbing with or without restart, random restart, and other variants. The solution representation, of course, was a vector of offset values. We had a number of tweak operators that were implemented in such a way as not to violate synchronization constraints. Here, in that case, synchronization constraints were of the following form. That set of executables must execute within n time slots of each other every so often. Okay. We applied that to a very large case study with 430 runnables, which basically yields a search space of 10 to the power of 27. So we're talking about very large input spaces. And this was the result, basically, where we went from a maximum CPU usage of 5.34 to slightly above 2 milliseconds. In that case, we could analytically compute what would be the minimum CPU time usage. And so we were very close. We could actually determine that we were very close from the minimum. So, of course, we compared our results with random search. We did the usual thing. Yeah. We compared the different search algorithms, but that's not that interesting. What was more interesting is that initially, we had simplified, our view of the problem was too simplistic. In practice, the car makers and the system integrator have to negotiate. It's not like they get synchronization constraints and they do their best. There is a negotiation process where, on one end, the car makers want, for example, a certain number of runnables to run close to one another, and the other guys, as I said, want to reduce CPU time usage. And so they have to negotiate whether those runnables can run within one slot of each other, 2 slots of each other, 3 slots of each other. And of course, the more you increase the number of slots, the less efficient and effective is the execution. But on the other hand, the more you save in terms of maximum CPU usage. And therefore, what those guys needed was a way to negotiate with each other in a somewhat rational manner. And all of a sudden, this became a bi-objective search problem, where what you want is to understand what is the Pareto form between CPU time usage and the number of slots, between runnables, the maximum number of slots that you allow, for runnables that depend on each other, and using those solutions on the Pareto form as a basis for negotiation. between the two parties. So that's what we did. We use NSGA2, and basically we generate, here is a Pareto front on our actual case study with 430 runables. As you can see, there are many solutions on the Pareto front. This is the Pareto front with random search. Again, we always compare to make sure that we are not solving an easy problem, that NSGA2 is useful. It does something. But of course, you cannot just show the Pareto front to users. But there are too many solutions. So we developed a tool that helps visualization and query analysis. I mean, nothing very fancy, but to help visualize actual solutions, I mean, the specific schedules, retrieve and visualize the result of simulations, and apply queries and solutions in order to further select solutions according to additional criteria. So to conclude on that particular design time verification problem, we were able with by objective search to help people make decisions and lower the risk of running out of CPU. And it was very effective. I mean, people before that were in great difficulties to determine what would be optimal solutions. So those are two examples, a test automation example, a design time verification example. I have applied in other projects, in other industries than the automotive industry, on different topics where I applied similar solutions. For example, in the oil and gas industry, on control systems, on offshore platforms, we use similar solutions to perform stress testing with respect to meeting task deadlines. So basically, we generate stress cases and we try to break task deadlines. That's one thing we did that worked very well, using search, Meta-Heuristic search again. We supported the automation of environment-based testing of real-time systems, where here the goal was to bring real-time system into unacceptable states, dangerous, unsafe states. So again, we use search to do that. We generated stress test cases in order to trigger concurrency faults of all kinds, deadlocks, races, yeah. And something for distributed systems, distribution-related errors. And in all those projects, basically, you had a common pattern. You had a problem, which was basically a fault model. You were trying to target certain faults. You had a model that captured information about the system and the test, its task architecture, whatever information is required to help guide the search. And of course, you had a search space, a search technique, and objective function. And the role of the model was to help guide the search, to make the search more effective. So the first lesson learned is that for many of those problems, if you don't have a model of a system of certain kind, then you cannot use search to solve your problem. You need additional information. You cannot just use execution information or whatever is available. Of course, the whole trick is to have sufficiently good guidance so that you traverse a small part of the input space until reaching what you're looking for. And that's where the whole trick of using Meta-Heuristic search is. Otherwise, you don't scale. The problem, of course, with Meta-Heuristic search is that extensive empirical studies are required. Since those are heuristics, since you cannot prove that they work effectively in an analytical way, you have to perform enormous empirical studies. I mean, and in our case, we are lucky enough that we have access for free to a high-performance computer at the university. Otherwise, we would be spending, thousands and thousands of dollars on every experiment. Yeah. So this is a limitation I'll get back to that, of Meta-Heuristic search, is that they require extremely large empirical studies that are very expensive and very difficult to perform. So let me get back to scalability and practicality, which was the starting point of my talk. So, as I said, based on my 20 years of experience, this is the most common verification challenge. And it's mostly ignored by most research papers, which is why we have a problem in using research results into practice. There are different kinds of scalability, human versus computational scalability, but both are important. When we talk about practicality, this is context dependent. So if we take those two examples, one about scalability, one about practicality. When we tested closed controllers, we were facing a large input in configuration space, and the way we made the strategy more scalable was to use smart heuristics to avoid simulations using machine learning and statistical models. That's how we did it. With respect to practicality, if I take the example of minimizing risk of CPU shortage, we realized that for the technique to be practical, we needed to support negotiations between the two parties. That it couldn't just be a single objective optimization problem. And only by understanding the context, the problem, by talking to practitioners, we could understand that and make our solution more practical. So lessons learned in terms of scalability. What's very important when you do software engineering research is that scalability must be part of the problem definition and solution from the start. It cannot be an afterthought or a refinement once you have devised a correct solution, which often is the pattern that you observe in research. People say, oh, I'm going to come up with a correct solution, and then I'll worry about scalability. Well, that never works. It has to be part of the initial problem definition. Because of scalability issues, it turns out on our project, and it's not a matter of personal choice, it was a matter of necessity, that we ended up to use on most projects Meta-Heuristics. Why? Because they were essential in order to obtain a scalable solution in most of our problems. We tried other things like constraint programming, like model checking. Never scaled, it never went anywhere. Okay? Even using professional constraint programming engines, like IBM Cplex or Comet, we ran out of memory, for example. But of course, the drawback of those solutions is that they only give you best answers within time constraint. There is no guarantees. Hence, the empirical studies. With respect to applicability, it's very hard to understand what makes an application applicable in a given context. It requires usually many weeks, sometimes several months of investigation to really understand the specific domain, the specific context. In our projects, it's very common that we spend up to 6 months just investigating the domain and the technologies in use before we start thinking about a solution. Because people usually are not able to just express their problems and their concerns in a clear fashion, in a spontaneous manner. It's really a work of investigation. You have to ask yourself questions like, what are the inputs required by the proposed techniques? How does it fit in the development practices? Is the output what engineers really require to make a decision? And of course, the answers to all those questions vary from context to context. Therefore, your solutions have to vary from context to context. So, to conclude with the discussion, based on my experience in solving various verification problems in various industry sectors, I found that Meta-Heuristic search tended to be versatile. That is, we were capable of adapting to different problems. Easy is maybe not the right word, but it was at least possible to adapt Meta-Heuristic search to different fault models, to different verification objectives. In general, the modeling requirements that were entailed were reasonable. When you do one problem, when you do model checking, for example, is that you have to build a very detailed operational model of the system with properties, for example, in temporal logic. the problem is that this is not a reasonable requirement. Not all environments are water. In our case, we needed model to guide the search, but those models were much simpler. For example, they were sequence diagrams with annotation, which is very different from detailed operational state model in model checking. Okay? Of course, as I said, the problem with Meta-Heuristic search is not a proof. There is no certainty. But in practice, when you try to use techniques such as model checking, which are supposed to help you prove properties, in practice, proof is an illusion. Why? Because when you devise a very complex operational model of the system, that model may be incorrect. And nobody can prove that that model is a correct representation of the system behavior. So if you cannot prove that the model on which is based your proof is correct, you have no proof, basically. So even though you can criticize Meta-Heuristic search for being a heuristic, in practice, proof is an illusion. So it's not like we are losing a lot by using Meta-Heuristics. Yeah. And I've already said that models are key to provide adequate guidance, as I've said before. So to summarize my talk, I presented a number of projects and 2 specific projects in great detail, where we use Meta-Heuristic search to enable scalable verification and testing. We have seen that we could handle quite a large variety of verification problems. The detailed example I provided were in the automotive industry. Scalability was a main challenge, and I've shown you how we dealt with it. And Meta-Heuristic came out to be a very handy tool to deal with scalability. Those examples I've shown you were actually used by practitioners. Those were actually solutions that were deployed within actual engineering groups. However, of course, Meta-Heuristic search is not the only component of a solution. You have seen that in the example I provided, but if I had had more time, I would have given you more examples. But the solution to the verification problems includes, in addition to Meta-Heuristic search, some form of system modeling, as I've mentioned, sometimes constraint solving. We have found in certain cases ways of adding or combining constraint solving to Meta-Heuristics, using them together to make the solution even more effective and more efficient. Machine learning, we have seen some examples where we use machine learning, and of course statistics. So usually, a complete solution involves all of those components, in addition to Meta-Heuristic search. So here is some applications of students who have contributed to some of the work I've mentioned, and colleagues. Thank you very much.
Yes. So, it's very interesting and very nice. One thing that I'm wondering, what do you come and do and how do you approach that problem?
My hearing is impaired, so speak a bit louder than usual. Sorry.
Okay, so just your opinion, how do you tackle the problem? Did you go into that? My car at this point has more than 15 or 16 or 20 controllers.
Oh yeah, more than that.
Those bloody piece of software and hardware talk together.
Yes.
And somehow part of the aspect is in the last task that you presented, the synchronization. But how do they deal about these plethora of things that need to communicate and synchronize, and how do you test them?
Well, so the question, for those who haven't heard, is related to the fact that on a typical vehicle, you have many electrical control units that run many controllers, and that some of those controllers will be interacting on the data bus of the car. Well, of course, here I haven't worked on that specific problem. I guess it's a bit like the difference between unique integration and system testing. You first have to test your controllers, and then you have to test the integration of the controllers. And basically, my guess is that you have to devise different test strategies. First, you test the controllers, like I've shown, and eventually you assume that those controllers, work correctly, and you basically exercise the communication protocol between the controllers on the bus. Yeah. So it becomes basically like testing a distributed system. And of course, then you have to have different test strategies that focus on possible interaction scenarios, worst case interaction scenarios between those controllers. But if you're asking me how they do it now, I don't know. It's not too clear to me. It wasn't too clear to me how they tested controllers anyway. I guess it's all based on domain expertise. It's not automated and it's not systematic. It's all based on individual talents. Let me say so. Yeah.
Yes. Follow up on that point, actually. I thought it was very interesting. This whole talk was great. And so I live in South Bend.
Sorry, speak a bit louder. As I told you, I have a cold and I don't hear very well.
Sure, and I can't necessarily speak that loudly. So I live in South Bend, which is mainly has mostly the parts suppliers for places like Detroit, the manufacturers here.
Okay.
And anyway, so I know some of the folks there, and they have just following up on the point you just made, they have a pretty serious problem where simulations don't actually match up to what the hardware is supposed to be doing. Because the hardware constraints are depending on heat and location and other issues. And so I'd be very interested in your comments on how to deal with that, because it is about expertise. Essentially, we've been doing it 30 years.
Yes, the way we deal with this, because of course I'm aware of the problem. So to repeat the question for everybody, the closed-loop controller testing strategy I've shown before was relying on the fact that we had models of the environment, so-called plant models. And what he was saying is that those plant models may not always behave exactly like reality, like real hardware. And it's true. What you can do in simulating, you can model the uncertainty in the plant model. You can account for uncertainty. So what we can do when we test is that we can test with a plant model that accounts for uncertainty. But then, of course, you have to do much more testing. I mean, because the space becomes much larger, the space of behavior of the plant. So, but that's one thing you can do. And actually, within the simulating tool, you have ways of modeling uncertainty of plant models. So that's the way we handle it. On the project here, we haven't tried to handle it. We use the plant models that were provided to us by our partners.
Yes.
So this actually probably is a follow-up to the last two questions. You talked about, Julio talked about sort of moving the issues of the distributed system. My understanding is that some parts manufacturers want to think about moving to multi-core in the ECUs because of the optimized power consumption ratio.
Yes.
That seems to introduce another level of complexity. They've got shared caches and so on. So all the scheduling information is dependent on how you use those.
Yes. For example, we can handle that. On the work we did on generating stress test cases to find schedulability issues. We can handle multi-core problems because basically, when you compute the fitness function, you run a scheduling component. And in our scheduling component, we account for the number of cores. It's one of the parameters. So if you have multiple cores, you can, for example, account for it when you compute the fitness function by having a scheduler that handles multiple cores. So there are ways of handling multiple cores. It's the same thing for what I've presented with respect to minimizing the risk of running out of CPU. You could account in your scheduling for multiple cores. That is your static cyclic scheduling would work. You could have an algorithm that works on several cores.
I think it's just that one of the issues though in that case, and this is the very domain-specific problem, is the worst case execution time of some of those executables doesn't take into account kind of worst case cache usage between the executables. So I guess that's more the data you're getting from the manufacturers has to be correct
Yes.
for the multiple contexts.
Yeah, but it's up to you then to refine your scheduler to account for it. Right. Basically.
Any other question?
Yeah.
I did, but we're close and I can see, I think we're at the end of the time and you definitely need some water.
No, that's okay. I can
And
do
then-
one more question. Or
Okay,
comment.
so I very much enjoyed your talk, and one of the things I was thinking about, though, was that the control engineers are very used to building models, and they're very good with tools like Simulink, and what would be your advice to an organization that wants to do this, but they're not necessarily in an area that's already modeled or where the engineers are used to building such models, and what would be your advice to those folks in that domain?
I have done that in the past. I worked with companies that were very different from the automotive sector. And we have basically used extensions of UML, or UML profiles. We have done that when I worked in the oil and gas industry, for example. But of course, the two examples I've detailed were from the automotive industry. And even the automotive industry now, they use CCML. We have projects where we use CCML because Simulink is only good at the controller level. But they need to model the entire system, not just the controllers. So they rely on CCML and extensions. So for the other problems when we have worked on outside the automotive domain, we use extensions of UML, but we try, of course, always to minimize the modeling requirements, try to make them as simple as possible for a given problem. Usually it can just be, for example, an extension of activity diagram, an extension of sequence diagrams with specific annotations for the problem at hand. And usually what you have to do then is to provide them with the modeling methodology. You cannot just tell them use that notation. You have to tell them, okay, here are modeling steps, where you start, what is the first step, the second step, what is the level of detail required for the modeling. And we do that usually. We always write reports and we provide tutorials with specific modeling methodology. I've done that many times, and I'm doing that with several of my partners right now.
Maybe just last question for you. It's really very interesting talk with Mohammed. There's practice. So my question regarding the queries that you mentioned, what type of queries are you using to explore the market solution?
It's not very sophisticated, it's very domain specific. For example, they know that there is a solution in Pareto front where a number of variables run within 3 time slots. And then they decide to add an additional criterion. They say, well, among the 3 variables, I really want those 2 variables to run within the same slot, at least every 5 milliseconds or every 50 milliseconds. They add additional selection criteria.
Oh,
you see what I mean?
It's not just queries like with the 2 objectives that they already considered in the beginning.
No, it's additional things.
Yes.
Additional selection criteria. That are not accounted for in the multi-objective search. You could, I guess, account them for, but then you would have 5 dimensions. And maybe that's not very useful, but it's just better to handle 2 dimensions and then do additional selection queries after that. Maybe it's good enough. It's probably maybe more practical than trying to handle many dimensions.
Yes. And also when you mentioned the OpenGPC regarding parameters, tuning, finding the right parameters, so there is a recent trend about hyper-heuristic where they try to find the best parameter for your problem.
Yeah, but the problem is that it depends on the problem. For the closed loop controllers, we cannot do that because computing the fitness function is too expensive. We cannot have hybrid heuristics and run hundreds of thousands of fitness calculations. It's not possible. What we tend to do is true. We tend to rely on simulation results in the literature. I mean, the Meta-Heuristic literature. There are you know, if you use techniques that have been well studied, you have a lot of simulation methods. We tend to use that. We also tend to do a bit always of sensitivity analysis. We vary a bit the parameters and we see whether or not it makes any difference. Yeah, and if it doesn't, we feel confident we're okay. But of course, that's another drawback. I had that on one of my slides of meta-heuristics. It's those parameters. That's why actually, for one of the problems, we try to use constraint programming. Because in constraint programming, you don't have parameters. It's an exhaustive search. Of course, we still need heuristics to determine the order of the search in an optimal way. But the problem with constraint programming is that it doesn't scale. You run out of memory. Yeah, it doesn't scale. So in one of the recent pieces of work I've done with a student of mine who is graduating now, we use meta-heuristics to find high-risk areas in the input space. And then we use constraint programming to study in a complete and systematic way the neighboring area around each solution. And it works very well, actually, combining the two. We get nearly the same efficiency as genetic algorithms and the same effectiveness as constraint programming. But you're right, so the problem is this is one of the challenges with meta-heuristics, all those parameters.
Okay, thanks so much. There is no question. Let's now we have a break of 2 minutes. Then we have session for today.
You, just out of curiosity, you got an HTML5 browser?
It was
I don't, because I just have Safari.